If you think you know how the universe is going to end, you're probably wrong. That's because no one knows for sure what the future has in store for us. And because, from big crunches to big rips, from cyclic revivals to periods of infinite darkness, the options appear limitless. But that's not to say that forecasting the end of the universe is beyond the capacities of science. By learning more about the universe around us today, we can uncover what will help us predict its ultimate demise. I'm Alex McColgan, and you're watching Astrum. Join me today on a journey to the future of the universe, a future where there are no longer any planets or stars or galaxies, no longer any atoms or molecules or life, a future where the universe is lying on its deathbed. How long do we have until that future is here? And is there an afterlife for the universe? These questions might sound impenetrable, but their answers lie in our understanding of the most familiar force of nature, gravity. Ordinarily, gravity is an attractive force that slows down objects trying to move farther apart, or speeds up objects moving closer together. That's why, before dark energy was discovered, astronomers assumed our expanding universe was being slowed down by gravity over time. They even came up with a parameter called Q to measure the rate of this deceleration. But at the close of the 20th century, measurements of supernovae revealed that Q was actually a negative number. The universe wasn't decelerating at all. It was accelerating. This acceleration is fundamentally tied to the type of matter and energy contained in the universe. If the energy of ordinary matter gives rise to a gravitational pull, it must take a very different form of energy to explain the gravitational push accelerating the expansion of our universe. We call this form of energy dark energy. The tricky thing is that we don't know what dark energy is exactly or where it comes from. And yet, the very fate of the universe is tied to its identity. Depending on the nature of dark energy, the accelerated expansion of our universe can grow stronger, settle down, or even reverse course. Rather than making a video on just one of these fates, we've decided to collect them all into one big flowchart to serve as your one-stop guide to the end of the universe. At the top of the flowchart is what dark energy is, and at the bottom is how we all die. Most cosmologists would agree that dark energy is likely to fall into one of two main categories. First, the most popular theory is that dark energy is the energy of the vacuum itself. Second, the leading alternative is that dark energy is the energy of new fields in the universe that we simply haven't discovered yet. Since fields are just a way to represent collections of particles, this would mean that dark energy is made of a new form of matter, new types of particles beyond electrons or quarks or anything else we know of today. From these two categories, our flowchart is going to branch out into theories of dark energy that are wildly different from each other and predict all sorts of catastrophic futures. On the vacuum energy side, we need to consider whether the vacuum itself is stable or whether it can jump into a state of even lower energy through a process known as quantum tunneling. A stable vacuum is by far the simplest scenario. It means that dark energy will continue to exist for an eternity in the same form it takes on today. Our universe will accelerate forever, growing infinitely larger and colder in what's called the Big Freeze. The good news is, you wouldn't notice anything changing here on Earth or even throughout the Milky Way, since there's enough mass concentrated in this small region to counteract the gravitational repulsion coming from dark energy. But if you zoom out beyond that, you'll notice that distant galaxies are being accelerated away from our own in all directions, eventually crossing a threshold known as the event horizon. Just like with a black hole, once you cross this point, you can no longer communicate or interact with the world you've left behind. That means that one by one we'll lose contact with all galaxies beyond the local few where gravity is strong enough to keep us close. All that will remain of them is a dimming, reddening light from the moments before they cross the event horizon. Eventually, this light will become so faint that it too will be unobservable, and future generations of astronomers, billions of years down the road, might have no idea that anything ever existed in the universe beyond the Milky Way.
If you're wondering what will become of the stuff inside the Milky Way, it dies a relatively boring death. The second law of thermodynamics says that systems will always tend towards states of higher entropy. When stars fuse hydrogen into helium and emit light as a byproduct, when planets heat up and winds soar across the atmosphere, and even when you eat a carrot and wait for it to come out the other side, all of those processes increase entropy. But the entropy of the Milky Way can only grow so large. Eventually, stars will run out of hydrogen to fuse, planets will be left to freeze, winds will abate, and there will be no more carrots left to digest. Matter will have nothing to do but collapse into black holes, and black holes will evaporate into a pool of radiation. What we once called the Milky Way will be in a state of total thermal equilibrium. Nothing will be happening. There will be nothing to happen. This fate that awaits the Milky Way is sometimes called heat death. Not because it's hot, in fact, it will be quite cold, but because there will be no more heat flow, no more temperature gradients, no more transfers of energy from one place to another. Admittedly, it might take a while to reach heat death. Some estimates place it 10 to the power of 106 years away, or 10 to the power of 96 times the current age of the universe. But if dark energy really comes from a perfectly stable vacuum, then there will be no avoiding it. Heat death is coming. There is one possible silver lining at the end of this story, however. It has been conjectured by Sir Roger Penrose, a Nobel laureate and brilliant physicist, that heat death might not be the end of our story, but merely a new beginning. In his model, known as conformal cyclic cosmology, Penrose proposes that the radiation-filled universe in the infinite future will be indistinguishable from the state of the universe at the Big Bang, and indeed, they may be one and the same. Each eon of infinite expansion in this model merely leads to a new Big Bang and a new cycle of cosmology. There isn't much evidence in support of this hypothesis as of yet, but it may be a source of hope to cling on to if our universe ends up heading toward a big freeze. You and I would not survive, but maybe the universe could, and at least that's something. If the idea of a big freeze scares you, I've got some good news and some bad news. The good news is that there are reasons to believe that even if dark energy comes from the vacuum, that vacuum state might not last forever, meaning we might not be headed toward a big freeze after all. One reason to doubt the stability of the vacuum comes from observations of the Higgs field. Current measurements from CERN indicate that the Higgs might have a lower energy vacuum state than the one we live in, though it could take something like 10 to the power of 100 years to tunnel into this preferred vacuum. To paint a mental picture of how this all works, we can imagine an apple falling off a tree, hitting our friend Isaac on the head, and rolling off into a small dip in the grass. A short distance away, there's an even bigger dip, which the apple would absolutely be drawn toward, if not for the barrier blocking its path. Classically, the apple is stuck, but quantum mechanically, the apple can and will tunnel through the barrier into this lower energy state, if you just wait long enough. The Higgs field works the same way, with its different vacuum states corresponding to the different dips in the grass. A second reason to doubt the stability of the vacuum actually comes from string theory. While string theory hasn't made any quantitative predictions, it's given us some pretty strong hints that stable vacuum states with positive energies are really hard to come by. String theory also predicts the existence of new fields that could conceivably tunnel to different vacuum states much faster than the Higgs, say within the next trillion or even 100 billion years. Here comes the bad news though. If we live in a metastable vacuum that can decay at the whim of a quantum mechanical fluctuation, we've got bigger things to worry about than the big freeze. Quantum tunneling into a more stable vacuum won't just affect the expansion of space, but it can also fundamentally alter the properties of particles and the laws of physics governing our universe. If the Higgs field falls into a new vacuum state, Ordinary particles like protons and electrons will have completely different masses, and atoms and molecules as we know them will cease to exist. Or if we tunnel into a new vacuum in the string theory landscape, our universe might suddenly contain new particles we've never seen before. In either case, life on Earth would all but certainly be toast. As for the universe as a whole, in this scenario, we can't predict its fate more precisely without more information about the new vacuum we fall into. Let's step back and take a look at the other side of our flowchart, where dark energy comes from the presence of new fields rather than the vacuum. There are different ways in which fields can evolve over time, which would in turn dictate the future trajectory of our universe. Unlike vacuum states, which would have perfectly constant energies between tunneling transitions, fields can continuously gain or lose energy over time. Just like a ball rolling across a rough patch of grass, fields experience friction as they evolve, so it's most natural to expect their energy to decrease. But physicists have shown that it's possible to have exotic types of fields called phantom dark energy that overcome this friction and actually gain energy over time. These exotic fields wreak absolute havoc on the universe. Because their energy is growing everywhere and all the time, they eventually overpower the energy from all other forms of matter, even within the Milky Way. This increase in energy heats up the entire universe, fully reversing course from all the cooling the universe has done over the past 14 billion years. In this scenario, the expansion of space doesn't just continue to accelerate, but it accelerates so fast that any region of space will grow to infinite volume in a finite time, maybe even just a few billion years from today. And if you want to call for help, that gets increasingly harder, as the cosmic event horizon we spoke about earlier will shrink down to the size of our galaxy, then our planet, then our home, and then us. As this is happening, the repulsive gravitational effects of phantom dark energy grow ever stronger, ultimately tearing apart all of the molecules, atoms, and nuclei in the universe into their constituent parts. Then, we hit the singularity. This new kind of singularity, where the universe is infinitely big and hot rather than infinitesimally small and hot, has been called the Big Rip. But I'm still hopeful that this grim ending from phantom dark energy exists only in the minds of theorists, while the real dark energy in our universe behaves more peacefully and loses energy over time.
So what would fate have in store for us then? Here's where our flowchart starts to get a little messy, because there are so many different ways a field can evolve over time. There are two main questions that have to be answered to predict the fate of the universe in this scenario. First, can the dark energy field have negative potential energy? And second, does the field's energy change slowly or quickly? If the field's energy is always positive and it loses energy very slowly, it would hardly be distinguishable from vacuum energy. In this case, we'd just be headed toward another big freeze. On the other hand, if the field's energy is drained away very quickly, the universe would soon have no dark energy left at all. It would stop accelerating, and its future would depend entirely on its spatial curvature, or the shape of the universe itself. A flat or open universe would eventually evolve toward heat death, but there would be no cosmic event horizon to prevent us from communicating with galaxies as far as the eye can see. This may be the most peaceful of all possible futures for the universe. On the other hand, a closed universe would eventually stop expanding, reverse course, and collapse back in on itself, which sounds less peaceful. This kind of recollapse is known as a big crunch. Having a closed universe is just one of two paths that can lead to a big crunch. The other way to see our Milky Way crushed to smithereens is for the dark energy field to reach a negative potential energy. At that point, it will only be a matter of time before the universe stops expanding and begins to contract. During this contraction phase, gravity turns cosmic friction into cosmic anti-friction, speeding up the field's evolution and giving it more energy rather than draining it. If the field gains energy slowly, there will be plenty of time for the universe to recollapse and experience a full-on big crunch. On the other hand, if the field gains energy fast enough, the universe could reach a temperature mimicking conditions at the Big Bang at a rate so fast that this would occur all before the Milky Way is even predicted to collide with Andromeda. Even though space does contract in this scenario, it doesn't crunch. In fact, the amount of contraction is hardly noticeable by the time Earth turns to toast. So what happens next? Models suggest that if the universe reaches extremely high temperatures while contracting, it could be forced to transition into a new phase of expansion where it has time to cool off once more. This transition is called the Big Bounce. In fact, the universe could go through a big bounce following a big crunch too. These scenarios open the door to a new type of cyclic universe entirely different from Penrose's idea, which we've discussed in previous videos, in which the universe goes through an infinite sequence of expansion, cooling, contraction, and reheating over and over again. In this picture, even our own Big Bang 14 billion years ago could have actually been a big bounce connecting our own cycle of the universe to all those that came before it. This wraps up our master flowchart for all the different ways the universe could end. It could freeze to death, be ripped to shreds, be crushed to oblivion, or simply heat up so quickly that it bounces into a brand new life cycle. We might not have any certainty yet, but even just narrowing it down to 4 possible options is already an enormous feat of science. So there's a great new topic for small talk, with strangers and dinner conversations. You're welcome. If you had control over the fate of the universe, which of these 4 destinies would you pick for it? Let us know in the comments below. Thanks for watching.